So yesterday, I told you how to find the transfer function of mechanical system, which were working in a linear state. So we talked about the translation motion of mechanical systems, and we obtained the transfer function of these systems. And I gave you a question. So one of you had given a reply, gave a solution, but I still thought to explain you how is transfer function of such systems obtained. So this was the example that I gave you yesterday, comprising of two masses m1 and m2 attached in the fashion as shown. So if you see, there are elements attached to it, such as a spring, dashboard, and friction is there existing there between the surfaces. So in order to find the transfer function, first of all, you'll have to identify what are the inputs and outputs. So in this particular problem, since it's given that x2, you will have to find the transfer function, which is the ratio x2 by f. So it's clear that input is f and output is x2. So it could have asked you about finding the transfer function in terms of x1. So in that case, that would have been, the question would have been like x1 by f. But since you will have to obtain the relation between x2 and f in order to find the final transfer function, so it's clear that x2 is the output. So in order to solve problems of such type, what you have to do is you will have to draw the FBD of the masses which are given in the system. So since you have two masses m1 and m2, then thus you will be drawing two FBDs of the systems. So we start with the free body diagram of m1. So always make a practice of making or drawing the free body diagram FBD of the mass on which force is being applied. So we prefer drawing FBDs of masses on which the input is given. So you could draw the FBD of M2 before drawing FBD of M1. That could be fine, but to make things more clear and to make things understand easily, it's better if you draw the FBD of masses on which forces act. So you're given a mass m1. So first of all, you try to visualize this system. So what you are going to do is you are going to apply input. You're going to give an input to mass m1 in the form of force. So this force is going to make this mass move towards right. So while this mass m1 moves towards right, the spring k1 will expand, while k2 will compress, and the dashpot, this dashpot will also compress, and this will also make the mass m2 to move towards right. So mass m will move towards right, it will make mass m2 move towards right, and will cause compression in the spring k3. Apart from these forces because of elements spring and dashpot, there are two more forces because of friction, which have coefficient fv1 and fv2 acting respectively on m1 and m2. So for the free body diagram of mass m1, you will first have to identify the input given to it, which is force Ft, which acts towards right. So since force is applied on mass m1 towards right, we'll be drawing this acting towards right, like this. And now you'll have to identify the resisting forces which oppose the main force F, and these forces act towards left. So these forces are because of the spring K1, because of spring K2, because of dashpot FV3, because of friction FV1, and because of mass M1. So there are in total 5 forces which will be resisting the main force F. So let us incorporate the resisting force one by one. So we'll first incorporate the force because of spring K1, which will be opposite in direction to the applied force F, and the amount of this force will be K1 times X1, where X1 is the net expansion of the spring. Now, because of spring K2, the force will be acting will be equal to K2 multiplied by X1 minus X2. Now, this is because for this particular spring, you have both the ends free to move, and these end moves with a different displacement. The left end moves with a displacement of x1, while the second end displaces by x2. Hence, the net compression that is going to happen within this spring is x1 minus x2, and hence the total force that it exerts on m1 will be k2 times x1 minus x2. Likewise, the third force because of dashpot fv3 will be because of friction. We first incorporated the force because of friction, and you can incorporate any other force apart from friction first, and next talk about friction. So Because of friction, we have a force. Since Fv1 is the coefficient b, and thus this will be proportional to the frictional force will be proportional to the velocity of the system of the mass m1, and hence the frictional force or the damping force because of friction will be b times dx1 by dt, or fv times dx1 by dt, and again in the opposite direction to the applied force. The fourth type of force which acts on the system is because of the dashpot fv3. And again, if you look at this particular dashpot on the left points, you have a displacement of x1, while on the right point of this dashpot displaces by x2. So the net expansion that is going to happen, the net compression that is going to happen within this dashpot will be x1 minus x2. And thus the force because of this dashpot which is resisting or which is acting towards left is again fv3 times d by dt of x1 minus x2, which is nothing but v1 minus v2. So you'll be talking about the net velocity that you will be observing within this dashpot, which is nothing but v1 minus v2. The fifth force which acts on this mass is because of its inertia, m1, and that will be equal to m1 times d square x1 by dt square. Now you mind this because we don't have things like x1 minus x2 in inertial force, because inertial force is something that will act on the net displacement that happens within the mass. So the net displacement that the mass will have is x1, and that is why the inertial force is equal to m1 times d square by dt square of x1. So if you now equate the force which is acting and while all the other forces that which are resisting, you get this equation, and we call this equation as 1. So F is the acting force which acts towards right, while all other forces are resisting and acting towards left and will be equated together. So I guess this is clear to all. If you have any problem in this particular equation, how this equation is obtained, you can ask me question. So now we talk about the FBD of the second mass. So from the FBD of first mass, we obtain the first equation, and we now draw the FBD of mass m2. Now if you look at this mass m2, the acting forces on this mass m2 will be because of the spring k2 and the dashpot fv3. Because the initial input which was force was applied to mass m1, this mass moved towards right, making the dashpot compress and the spring K2 compress, and will further make mass M2 move towards right. So the force that will be directly acting on mass M2 will be because of spring K2, and that will amount to K2 times x1 minus x2. And the second force that will be acting on mass M2 and will be trying to move it towards right will be because of dashpot FV3 times V1 minus Vt, or d by dt of x1 minus x2. So these two forces are acting on mass M2 and will try to move the mass towards right. Now, apart from this, there are three resisting forces which acts on mass m2 and will resist the acting forces, which are because of the spring K3, because of friction Fv2, and because of inertial force, which arises because of mass m2. So the first force which acts towards left is resisting is equal to K3 times x2. So x2 is the net compression that will be observed in a spring K3 because the other end is fixed. The second force because of friction will be Fv2 times V2. So since you are going to have a velocity of this mass m2 as d by dt of x2, which is v2, and hence the damping force or the friction force will amount to Fv2 times d by dt of x2. Third type of force which will act on mass m2 will be inertial force acting towards left, which amounts to m2 into d square by dt square times of the net displacement this mass is going to have, which is x2. So these are all the forces that will be acting on mass m2, and now we are going to equate the acting and the resisting forces together, so we obtain equation 2. So on the left hand side of this equation 2, we have acting forces which will be equal to the resisting forces. So now from equation 1 and 2, if we take the Laplace transform of both the equations, so for equation 1 we obtain on taking Laplace transform as f equal to, so if you look at equation 1, which is this f equal to in time domain. Small f is in time domain, x1 is in time domain, so all the small letters are in time domain. And once you take the Laplace transform of this equation, you get capital F, which is in S domain or Laplace domain. So capital F will be equal to K1 capital X1 plus K2 capital X1 minus capital X2 plus FV1. And now you have first derivative of x1, which in Laplace domain will be written as S times x1. So if you look at this equation, you have S times x1 of Fv1. Likewise, FV3 d by dt of x1 minus x2 will be written as FV3 s times x1 minus x2 in capital. So this is s times FV3 x1 minus x2, and corresponding to mass, because you have double derivative now here, and this will be written as s square m1 capital X1, which is written over here. So again, reminding you that since we're trying to find the transfer function, it was mentioned that whenever you try to find transfer function, you will have to assume all the initial conditions to be zero. That is why we are not considering any initial condition while taking Laplace of derivatives or integral. They're all assumed zero. That is why you don't see in equation A any initial condition. Now likewise for equation 2, if you take Laplace transform of equation 2, so you get k2 capital X1 minus x2 written over here, and this becomes s times fv3 capital X1 minus x2 equal to k3 x2 plus s fv2 x2 s square m2 x2. So this is equation B. So if you solve equation A and B, since you want to find the relation between ft, the input, and the output xt, and since if you look at equation A and B, you'll see that there are three variables. One is f, the other is x1, and third is x2. You will find three variables in both the equations. So your task now is to eliminate the variable which is not required. So x1 is not required. You require only a relation between f and x2 because x2 is the output. So you will try to eliminate x1 using both the equations A and B. So from equation B, if you look at equation B, you can obtain the relation in terms of x1. So taking all the terms associated with x1 on leftmost side, so we get this relation. So if you take the relations corresponding to x1 together, you get this, and all the remaining relations are of x2. Now if you further simplify this, you get x1 taken together, x2 taken together, and you get a relation x1 in terms of x2 as equation C. And if you put this equation C in A, so since the relation A was between f and x2 and x1, so you had all the three variables in equation A. So equation A can further be simplified as f equal to this x1 minus this x2. If you put this value from C, the value of x1 in terms of x2 in this particular equation, what you get is this way. So now you obtain a relation that is in terms of x2. So you have an input f in terms of x2. Now you take all the elements associated with x2 together, then you find the ratio x2 by f, which is nothing but the transfer function. So you obtain this relation, which can further be simplified, and I leave this all up to you. So this is your final transfer function. So I guess this is clear. Now, yesterday I talked about rotational motion. I told you that a similar relation exists for rotational systems as well. So now you talk about in place of force, you talk about torque. In place of linear displacement, you talk about angular displacement. In case of in place of linear velocity, you talk about angular velocity, and in place of linear acceleration, you talk about angular accelerations. And the relation are given as this forms. And I told you it's supposed that both the ends are free to move in all the three cases, in all the two cases. So inertia is the mass is rigid, so you don't have both the ends free to move because you assume that this is not the mass is not flexible; it's always rigid. So in this particular spring, if suppose that you applied torque on the right hand side, and this torque allowed the right point to move or displaced by an angular displacement of theta1, while the left point rotated by a displacement theta2, then in that case the torque is given by the relation k times theta1 by theta2. Because if you're going to observe, the net angular displacement going to happen within the spring will be theta1 minus theta2, and that will correspond to the net torque produced by the spring. So if otherwise you left the uh, left end, the other end free to rotate, you didn't have any mass attached to it or any system attached to it, Then considering that spring is massless, an ideal spring in that case on application of torque will allow both the points right and left to rotate with the same angle, and hence no torque or no relation will exist. So you have both the angles with displacement with same values. In that case, t will be 0. But we assume that there is a mass or a system attached on the left hand side which will allow the spring to rotate with a different displacement on left point compared to the right one, and hence the net torque or the net rotation in the spring will be observed as theta 1 minus theta 2, and will be exerting a torque equal to k times that net orientation or displacement. In case of dashpot, if you're going to use this in a rotational system, now the torque which will be equal to or proportional to the angular velocity of the motion. So now you have a net displacement difference in the displacement as theta 1 minus theta 2, and in that case you get t equal to the torque because of dashpot or viscous damper will be equal to d omega 1 minus omega 2, where omega 1 is the angular velocity of right point and omega 2 is the angular velocity of the left point, and thus you get d times d into first derivative of theta 1 minus theta 2, which is nothing but the net displacement or the net difference in the displacement between the 2 points right and left. So now we are going to use a different abbreviation and different syntax for the damping constant in case of rotational motion, while in case of linear motion we were calling this as B. And this spring constant should have also been written as k theta, because but the book used it as k, so I've also used this as k, but I guess it's better if you call this as k theta because it differs from the linear or translational spring constant k. So this is torsional spring constant k theta. Now in case of inertia, if you are going to apply a torque, and this torque will cause this mass to rotate with an angle of angular displacement of theta. So you have the rotational or inertial torque, which is given as JL. Sorry, it's a correction. It should not be alpha minus alpha 2. So you don't have flexible mass. It's only a single mass. So in case of inertia, if you have a mass with moment of inertia j, in that case the torque will be given by j times alpha. Alpha is the angular acceleration this mass will be observing because of application of torque t. And thus this will be given as j times d square by dt square of the angular displacement taking place for this mass or a moment of inertia j. So I guess this is clear. Any questions? Now we start doing an example. Suppose you're given a rotational system comprising of two masses with moment of inertia J1 and J2 attached in this manner. So you have two dashpot and a spring connecting both the masses J1 and J2, and the two ends on both the side of dashpots are fixed. And suppose that we apply a torque at this particular point. So this point is attached to the mass J1. So you are in fact applying torque to the moment of inertia J1 or mass M1, which has moment of inertia J. So we first, in a similar manner that we did in translation motion, will draw the free body diagram of J1. So now we'll observe how many forces are acting to it and how many are resisting. So we see that in this particular system we have only one acting force acting on J1, and on this particular mass the resisting force will be because of the dashpot D1, because of spring K, and because of its own moment of inertia J1. So we'll first draw the acting force torque, which will be acting anti-clockwise. So if you look at this mass on from the left hand side of the system, or if you look at the left hand view of this system, you'll see that this J1 will, the cross sectional view of J1 will look something like this, and the torque will be acting anti-clockwise. The resisting forces will of course be opposite to the direction of acting torque, which is clockwise. So we draw the first resisting force because of dashpot or damper D1, sorry, because of spring. We'll first draw the resisting force because of spring K, which is nothing but K into theta 1 minus theta 2, the net displacement, angular displacement happening in this particular spring, because this point displaces by theta 1 while this particular point displaces by theta 2, and hence the net displacement that is going to happen within this spring will be theta 1 minus theta 2, and thus the torque that this spring will exert or resist the mass m1 with moment of inertia j1 will be k times theta 1 minus theta 2. The second resisting force is because of damper d1, which is nothing but d1, the constant, multiplied by the angular velocity omega 1, which is nothing but d by dt of theta 1. So you'll observe that because the other end of this dashpot is fixed, so it is going to the other side, the right side of this dashpot will observe an angular velocity omega 1 only. And the third resisting force will exist because of moment of inertia J1, which is J1 times alpha 1, which is d by dt square of theta 1. So T is acting while all the three forces are resisting, and hence we equate them to form the equation. We obtain the equation T equal to K theta 1 minus theta 2 plus J1 d square theta 1 by dt square plus D1 d theta 1 by dt. So this is something that you can obtain using Newton's laws as well. So there's nothing new in this, and the way we are trying to solve this is called as D'Alembert's principle, which does nothing but equates all the acting and resisting forces together. And D'Alembert's principle consider the inertial force or inertial torque to be resisting force or torque as well. Now, if we try to draw the FBD of mass m2 having moment of inertia j2, so in this case, the acting torque will be because of the spring K attached to it. So, since you're applying torque to this system at J1, this J1 will rotate anticlockwise, will cause this spring to have a motion anticlockwise, and thus this spring will exert a force or a torque on J2 anticlockwise in this manner. So the net torque that is being exerted on J2 will be K1 times theta 1 minus theta 2. Since the torque that exists or the tension that exists within this spring is K1 theta 1 minus theta 2 throughout. Note that this particular torque was resisting in case of J1, but it is acting in case of J2. So the resisting torque in case of J1 becomes acting in case of J2. Now the resisting torque on J2 will be because of the dashpot B2, which has a net angular displacement of theta 2 on one side, and hence the torque is given as d2 times omega 2 or dt by theta 2. And the other is because of moment of inertia J2, opposite in direction J2 times alpha 2. And now again we equate all the acting and resisting forces together to obtain the equation given as K. So this should be K, not K1. This is K, not K1. So K theta 1 minus theta 2 is the acting force, and the resisting force are because of moment of inertia J2 and because of dashpot D2, and thus we obtain equation 2. So from equation 1 and 2, if you take the Laplace transform of both the equations, we get them as A and B. So this is the Laplace transform of equation 1, this is the Laplace transform of equation 2. So again, looking at the equation that you obtained for the equation 1 was given as this. So if you take the Laplace transform of this equation, all the derivative that are involved in equation 1 will be changed into some terms of the form of S. So this is what you have in equation A. So you have the terms of S in place of derivatives. So second derivatives gives you S square, the first derivative gives you S. Likewise, if you take Laplace transform of equation 2, you get this as K theta 1 minus theta 2 S square J2 theta 2 plus S d2 theta 2. So this becomes Laplace transform equation, can be solved easily. So from this you get on simplifying equation A and B, you obtain the torque in terms of theta 1 by putting the values of theta 2. Since now you want to find the transfer function by obtaining the relation between t and theta 1. So you see this in the question that was given. So in this question, it was given that find theta 1 by t. So theta 1 in this case is output. So theta 1 is nothing but the angular displacement that J1 observes. So you will try to eliminate theta 2 in this particular system or the equation that you obtain. So if you look in equation A and B, you will be eliminating theta 2. So this can be done by obtaining theta 2 in terms of theta 1 from equation B and then substituting this in equation A to obtain the final equation in terms of theta 1. So you obtain torque, the relation of torque with respect to theta 1, and from this you obtain the transfer function as follows. So theta 1 is the output, T is the input, you get the transfer function given it. So I guess this explains. Now there are two more problems that I leave upon you, and I'll be asking you to submit this as home assignment later on. I will provide you the dates, but you keep in mind, and it's better if you solve them as early as possible so that they do not accumulate as a problem later on. So these will be given to you as you will be submitting this as home assignment. So it's better if you take a snapshot of these questions. Well, in fact, I'll be uploading the video of today, lecture 8, and you can obtain these questions from that video as well. So now, the third type of mechanical system under consideration is the combination of translation and rotation systems. For example, you have a rack and pinion arrangement where you will be applying torque to the pinion and observing a linear displacement on rack, or you will be applying a linear force to the rack and observing an angular motion of the pinion. So the example of which is the steering system of vehicles. So in a steering system, you steer by a steering wheel where you apply torque to the steering wheel and try to move the wheels which are attached to the rack linearly on right or left. So that can be explained if time permits. So you can see this on yourself using the references on internet that how the steering and the vehicles are done. So suppose that this is the schematic of the rack and pinion. You have pinion and the rack with, let's say the mass of the rack or the mass attached to the rack is m, and on application of a torque T to the pinion will cause this mass to move or displace by a displacement x. Now the task is to find the transfer function or the relation between output x and input t. So we again will draw the free body diagram of pinion and rack separately. So for FBD of pinion, we observe that the torque which is being applied clockwise to the pinion will have a resisting torque, assuming everything to be ideal, assuming that there is no mass of pinion, there is no friction given to the pinion, or there is no friction acting on the rack, and the rack is having only mass m. Then in that case, in ideal situation, we say that the torque which is acting on the pinion will have a resisting torque only because of the rack attached to it. So the rack will exert a force on this pinion equal to R cross F, where F is the force acting on mass m, and thus this will be resisting in nature, resisting to pinion. And again we draw the FBD of rack. So rack will be having the force acting on the mass towards right, while the resisting force will be because of the inertia of the mass. So we don't have friction acting on the rack, we don't have any spring attached to it. So the only thing that will cause the motion to be opposed is because of the inertial force md by dt square of x. Now if we obtain the relation, so we have t equal to r ft, so they are function of time now, and from FBD of the rack we get force equal to md square by dt square of x2. Now if we take the Laplace transform of both these equations, we get torque as a function of s. So they are Laplace transformed functions, and equation A is obtained from 1, equation B obtained from 2. If we equate these two equations, we obtain the transfer function as x output by input torque, which is equal to 1 over s square Rm. So this is the required transfer function of the rack and pinion arrangement. And of course you can have many more translation plus rotational systems, combination of them, like using pulleys and belts and conveyor systems. So they are all examples of translation, combination of translation and rotational systems. So you can do those examples by searching it in books. Normalized Slice, I think, has skipped this part, the translation and rotational system, so you can search it on your own on other books using Google Books, the website. So the next topic is gear trains, and we'll study about this in lectures.